charge in front of a grounded, what that means is potential there is 0, metallic plane. Plane means it's of infinite extent. So, let me specify the problem. What the problem is that I have a plane which has been grounded. That means potential out here is 0, and I put a charge in front of it, q, at a distance, let us say z0. What is the potential throughout? Notice that this has been grounded, and so this line, this forms one boundary, and all over the place up to infinity, let me just make it up to infinity, there the potential is 0. So, I have actually specified potential all over the boundary. I want to know what is the potential, let us say at V equals x, y and z. Since this color is not okay, let me write a different color, x, y and z. I have already written this to be z naught out here. So, I am assuming that this direction is z. To make you visualize things better, let me make it in the conventional sense. Here is my boundary, here is my z axis, and here is the charge q at a distance z naught, and I want to find potential V x, y, z. In this volume above, let me make that with this color, because this specifies the boundary of this volume, right. Now, inside this volume, the Poisson's equation is del square V equals minus rho over epsilon 0. Recall what rho is given for a point charge as. This is given as delta function. So, q delta r minus z naught z over epsilon 0. And V is 0 at z equal to 0. This is a z equal to 0 plane, and all throughout outside, and at r equal to infinity. All right. I want to find the solution of this. Now, one way of course is to solve the Poisson's equation. Other way, can I find a charge configuration so that this boundary condition is satisfied? If I can do that, then I found my solution, the solution. All right, and that is the trick that we use in method of images. Now, just a couple of points. One, this potential is not going to depend on the where I am on the xy plane, right. So, it has cylindrical symmetry. So, it depends only on the distance x square plus y square is proportional to x square plus, not proportional to, depends only on x square plus y square, right, and it's obviously going to depend on z naught. So, now let us look at this plane again, and now we are going to have a moment that will tell us what method of images looks like. Here is the charge q, and I want potential of the boundary to be 0. Now, look at this. If I think of a charge behind this plane, which is minus q, exactly at the same distance, then q gives me potential on the boundary as 1 over 4 pi epsilon 0 q over square root of x square plus y square, because the charge is at x and y equal to 0, plus z minus z naught square at z equal to 0, because this boundary is at z equal to 0, and minus q gives me a potential 1 over 4 pi epsilon 0 minus q over square root of x square plus y square plus z plus, it's at minus z naught, 0 square at z equal to 0. So, although the two give different potentials at different points, but at z equal to 0, the two potentials are equal and opposite in sign. and therefore at this immediately tells me that at z equal to 0, V is 0. Right? If at z equals 0, V equal to 0, that means these two charges plus q and minus q give me the boundary condition that is required. Naturally, obviously, far away at r tending to infinity, both charges give me 0 potential. So, r equals infinity condition anyway satisfied. The beauty is that even at z equal to 0, the boundary condition is satisfied. Therefore, if I look in the upper region, which excludes this charge, then Poisson equation in the upper region is del square V is equal to minus q appropriate delta function over epsilon 0. So, as far as the upper region is concerned, the potential, which is a combination of these two, satisfies the same Poisson equation as it satisfies only for the upper charge, and the two together give me the same boundary condition. That means in the upper region, if I write the potential, so let us take plus q here, minus q here. In the upper region, if I write the potential V x y z as potential due to q plus potential due to minus q, then del square V is equal to del square V q plus del square V minus q, but for the upper region this is 0 because delta function gives me 0 in that region. It satisfies the same Poisson equation as del square Vq is E. All right, and they also satisfy the boundary condition. So, the combination Vq plus V minus q satisfies the correct Poisson's equation and the correct boundary condition. What that means is that this is a solution that satisfies both, and this is the solution then by uniqueness theorem. So, we found the solution. That means for a charge in front of a grounded metallic plane or grounded plane, if I put a minus charge here and write the potential in this region as summation of V due to q plus V due to minus q, this is the solution. And this is the idea behind method of images, that if you found a solution by putting some image charges somewhere, you found the solution. And therefore, I can write potential V x y z as is equal to 1 over 4 pi epsilon 0. Q is the same for both, so I can even write q outside, 1 over x square plus y square plus z minus z naught square root minus, and that is due to image, 1 over square root of x square plus y square plus z naught whole square. This is the potential. Once I have found the potential, rest everything follows. If I want to find the electric field E, x, y and z, this comes out to be as minus gradient of V. If I want to find the charge on the surface, I will find the electric field here, and by Gauss's law relate it to the surface charge. So, let us do that. Let us, using this, find the charge on the metal surface. Right? So, what we want to do is, we have found V, which is equal to x, y, z, which is equal to q over 4 pi epsilon 0, 1 over square root of x square plus y square plus z minus z0 square minus 1 over square root of x square plus y square plus z0 square. Then the electric field, let's write this slightly differently because this comes in the combination of x square plus y square, which using cylindrical coordinates I can write as s square. So I will write this as q over 4 pi epsilon 0 1 over square root of s square plus z minus z0 square minus 1 over square root of s square plus z0 square. Electric field E x, y, z, and let's find its z component only is minus, you will see in a minute why I am doing that, dV over dz is going to be q over 4 pi epsilon 0. This gives me minus 1/2 times, there is a minus sign outside, 2 z minus z0 divided by s square plus z minus z0 square raised to 3 by 2 minus minus plus 1/2 2 z plus z0 over s square plus z0 square raised to 3 by 2. This 2 cancels. So I end up getting, I can also remove this minus sign with this minus sign and put a minus sign here. So I end up getting E z as equal to q over 4 pi epsilon 0 z minus z0 over s square plus z minus z0 square raised to 3 by 2 minus z plus z0 over s square plus z0 square raised to 3 by 2. Why I am calculating Ez only? Because that is required, that is the only thing that is required for the charge. Since this is an equipotential surface, the grad, we have already discussed, the gradient is going to be perpendicular here, and therefore near the surface the field is only z component. Let us see what is the charge density. If I take a small box here, all right, then the area on this side of the box is going this way. Field inside, since this is a metal, field inside is 0. This side area is perpendicular to the field, so therefore this will not contribute. So I get E dot ds as Ez times this small area, let us call it delta A. And this should be equal to charge enclosed, sigma delta A over epsilon 0. And therefore sigma is equal to epsilon 0 Ez at z equal to 0. Putting it here gives me sigma at distance s or xy for charge at z naught is equal to epsilon 0 times this at z equal to 0. So q over 4 pi epsilon 0 times, you can calculate this very easily, it comes out to be minus 2 z naught over s square plus z naught square raised to 3 by 2. All right, so now this epsilon 0 cancels, this 2 gives me 2 pi here, and therefore you can see that charge on the surface is sigma s is equal to minus q over 2 pi z0 over s square plus z0 square raised to 3 by 2. The charge, as you go away from the position of the charge, let us say this is distance s, it starts going down. All right. So, charge density goes down. Charge